Hi, my name is Skorokhodov, and in this video I will talk about our joint work with Savvy Ignatiev and Mohamed Al-Hosseini, adversarial generation of continuous images. A typical paradigm to represent an image is to represent it as a 2D array of RGB pixel values. But there is another paradigm which appeared recently and is gaining popularity: implicit neural representations. It views an image as a neural network. We say that an image is positioned on a 2D coordinates plane. And to compute image color in some coordinate, we pass this coordinate into a neural network. And the neural network predicts the corresponding RGB value. We can obtain the pixel-based representation of an image by evaluating the neural network in each location of the coordinates grid. In this way, a single neural network corresponds to a single image. There are several benefits of such a representation. First, it captures the true continuous form of the underlying 2D signal. Second, it provides compression for higher resolution. Third, it is more universal, since we do not restrict ourselves to any image format or aspect ratio. And finally, we can use inherent properties of neural networks for additional image manipulation. So in our work, we built INR-GAN, a neural network generator that produces images in this implicit neural representations form. A traditional convolutional generator is typically structured the following way. It samples input noise and passes it to a sequence of the convolutional blocks, which outputs a pixel-based representation of an image. The INR-based generator is designed differently. It samples input noise and passes it to a fully connected neural network that produces the parameter vector. This parameter vector is then plugged into an INR, a neural network, which is evaluated at each location of the predefined coordinates grid. And this gives us the pixel-based representation of an image. To make the generation process more efficient, we developed two techniques. Factorized multiplicative modulation splits the parameter vector of an INR into the variable part produced by the generator and the shared part, which is common across all INRs, and they are combined in a specifically designed FMM linear layers. Multiscaling assumes that after we produced the parameter vector and plugged it into the generator, we compute the final image on the sequence of the coordinates grid of progressively higher resolution. This allows to save computation at earlier stages of the generation process. Employing these techniques allows us to outperform existing INR-based decoders and almost match the performance of the convolutional ones. But the true power of the INR-based generator comes from its inherent properties. The first one is meaningful interpolation. Compared to pixel space interpolations, interpolating in the parameter space of INRs allows to preserve the semantic properties of the image objects. The second property is out-of-the-box super resolution. After we trained our generator on the image collection, we found that it can perform super resolution out of the box. Another property is out-of-the-box extrapolation. After computing the original frame, the INR-based generator can extrapolate it outside its boundaries by computing color values in the positions outside the original coordinates grid. Another property is better understanding of image geometry. We trained a linear model to predict key points from latent codes for two models, StyleGAN2 and INR-GAN, and found that for INR-GAN the test accuracy was substantially higher. This implies that our generator stores geometric information in a less entangled and more accessible way. You can check other experiments and explorations that we did in our paper. Thank you for your attention.